Hello, welcome back. In this segment, I will introduce the notion of extension fields. It's an important concept we need for AES, for example. Instead of doing arithmetic in set of numbers, in the extension fields, we will be doing arithmetic with set of polynomials. Okay. So in the previous segment, we talked about Galois field. I used Z2 as an example, right, with elements 0 and 1. And we proved that Z2 is actually a Galois field. We denoted it by GF of 2, the same thing as Z2. And in this segment, we will extend this idea to another field called extension field. So instead of elements as numbers, we will have elements as polynomials, okay? But not any generic polynomial. Polynomial whose coefficients are just zeros or ones, okay? So for example, the polynomial can be x7 plus x3 plus 1, okay? This is a polynomial. It's a valid polynomial because the coefficients are either 0 or 1, okay? For example, there is no x5 or x4. The coefficients are 0 in that case, okay? So this is the type of field that I'm going to talk about, is bunch of polynomials, okay? X4, X2, X1. This is a polynomial. Okay. So you have a set of all polynomials, and we will be defining operations in that set. You remember, for a field, we need two definitions, two operations. One is the plus and the multiplication. So we can easily add polynomials, of course, and we want the result to be also a polynomial, which is true. When you add two polynomials, the result is also a polynomial. And when you multiply two polynomials, the result is also a polynomial. In the case of finite field, we need to make sure that the result is an element in the set. Okay, so extension fields that we deal with are finite sets. That means we need to define the operations plus and multiplications more precisely. Okay, let me start defining plus in this segment. But before that, we have to understand how to represent polynomials in a computer. Okay, so one easy way to do is simply use the coefficients, right? The coefficients are either 0 or 1. So let me show you how I will represent this using a byte, okay? The 7th position is turned on, right? Because there is 1 in the front. So I'll put 1. And the 6th position is 0 because there's nothing there. 5th, 0. 4th, 0. 3rd is 1. 2nd is 0. X is 0, right? And then your constant is 1. Okay, so this is how you could represent a polynomial using a number like this. Okay, we don't have to explicitly say x power 7, x power 3. We can just represent as an integer, and depending on the bit positions that are turned on, we know exactly how to convert this into a polynomial. Okay, so this is, let's say this is a polynomial b or p, and if you have another polynomial, let's say this is polynomial q, how would that look like? 4th position is turned on, right? We start with index 0. And the 2nd position is turned on, and the constant is also turned on. Okay, so the rest are all zeros. This is how we represent polynomials. Okay, so this is polynomial q. So more generally, suppose you know a polynomial has, say, a degree like this. For example, I'm going to represent this as a polynomial in power 7, right? X power 7, a6, x power 6, and so on, some a0. Okay, so these coefficients a0 through a7 can either be 0 or 1. That's the Galois field elements. So every polynomial is just, we can view it as a vector, a7 all the way until a0. So how many such polynomials will be there? If we assume the degree is at most 7, then you can see there are 8 elements, right? a0 through a7, 8 elements, and each element can be either 0 or 1. That means if you were to write all possible polynomials, you will generate easily 2 power 8 possible polynomials, which is 256. Okay, so there are 256 possible polynomials you will have of degree at most 7. Okay, so 7 is just an arbitrary example. Okay, you can have in the AES case, we deal with A0 through A7, but in other constructions, there are polynomials of higher degree. Okay, but I just want to give you an impression of how you would represent a polynomial using a bit vector, like the one that we just talked about, P and Q as examples. Okay, so I will show you how to model this in a computer program, like Python program, for example, very quickly. Suppose you have a number A. Okay, this is Python, so you don't have to declare data types like unsigned, signed, and so on. But the idea is pretty much similar in other languages as well. Suppose you have a number A and you would like to turn a particular position to be on. Then the trick you could do is simple. Take the number one. Okay, the number one is interesting because the bit pattern of one is ending with 1. Depending on the word size, it can, you can count how many zeros you need up front, but let me just mark it as like this. So there will be a lot of zeros in the front, and that's 1. Okay, and suppose you would like to turn on, suppose your A is, let's say A is 0. Okay, and you would like to turn on the third position of A. So what you will do is you move your 1 to third position. So this is 1, 2, and third position, right? So basically you are left shifting. This is called left shift operator. Okay, so you're moving your 1 3 positions to the left. So you will have your 1 followed by 3 zeros because you moved 3 positions to the left. Okay, and then you'll have a bunch of zeros. Okay, so this is the result of 1. You're left shifting to that many positions. Now you do bitwise OR. This is bitwise OR with your A. So A itself is 0, right? So A has 0. Everywhere it's 0. But if you now bitwise OR, this is bitwise OR, the 1 will be turned on and the rest all will be zeros. Okay. So you have essentially turned a particular position of A to be 1. Okay, that's the purpose of the set bit routine. Okay. Set bit routine takes a number and a position to be turned on, and it uses this little trick with left shift operator and then combined with the bitwise OR to turn on a particular position. That's how you can create a polynomial. Okay, let me show you a demo now very quickly. I will now show you how to model a simple polynomial. Let's say the polynomial is, so this is how you do. Suppose I say A is a polynomial, okay, A equal to 0. I need the 7th position to be on, right? So I'll say 7th position turned on. And then 2nd position, not the 1st position, 0th position. This is x power 0. Okay, x power 0 means 0th position. 0 corresponds to x power 0, which is what exactly we need to represent the constant 1. Okay, so now if you print A, you will get an integer, of course, 133, and I'll show you the binary representation of 133. Now you can see here I have 4 plus 4, 8 bits. The 7th bit is turned on. That's exactly we need for x power 7. The 2nd bit is turned on, 0, 1, 2 is turned on, and then say the 0th position is turned on. You're starting from 0th position to a 7th position. Okay, so this is how you would represent a polynomial using a simple integer like what I have shown you. Okay, Python automatically takes care of long integers, so we don't have to worry about big integers. Like for example, we can even represent 127. For example, if you have x power 127, usually you can't use regular integer or long integer to represent 127, but Python has the notion of big integer that will expand automatically, so don't worry about that. Okay, all right, so this is how you would represent a polynomial as an integer. Okay, now let's go back to the whiteboard and finish up a few more things quickly. We know how to represent polynomial in a number using an integer. We can easily do addition of polynomials. Okay, p plus q, how do you add two polynomials? It's simple. You add the corresponding components of the vector. Suppose your polynomial is p and the q. In this case, you add, you apply bitwise exclusive OR. Okay, let me tell you why we need a bitwise exclusive OR. 1 plus 1 is 0 in GF of 2. Okay, just because we do mod 2, and exclusive OR takes care of that automatically for you. And why do we need to cancel out? Because if you add these two polynomials, x power 7 plus x power 4 plus x power 3 plus 2, but there's no notion of 2 in our Galois field. 2 has to be converted into mod 2, which is 0. Okay, so addition of two polynomials just correspond to bitwise exclusive OR, and that will take care of Galois field addition. So all you're going to do is take two polynomials and add the corresponding positions using bitwise exclusive OR. Okay. If let's say I introduce x power 3 here for a moment. Let's say I have x power 3. So now what will happen in this case? The x power 3 and x power 3 should cancel out, right? When we add these two polynomials, this is automatically taken care because x power 3 will be, this position will be 1, right? And now if you add a bitwise exclusive OR, this will be 0, which is exactly what we need because x power 3 is present here, x power 3 is also present here. Okay, so we know how to do polynomial addition. And the interesting thing is that polynomial addition will give you a new polynomial, and the degree of the polynomial will not increase. It may decrease. Let's say x power 7 is present in both places, then it will go away. But the resulting polynomial is still a member of the set of all possible polynomials. So when you add two polynomials, the finite field property that under addition holds true. Okay, so it's closed under addition.